This lecture is about the Tseitin transformation. The Tseitin transformation is a linear transformation from an arbitrary propositional formula to CNF, preserving satisfiability. And it goes back to a paper by Tseitin from 1966. And this Tseitin transformation is used in all current SAT solvers. The key idea is that we do not try to find a formula which is logically equivalent to phi, but we add extra variables. More precisely, we give a name to every subformula except for laterals, and we use these extra names as fresh variables in our formula. So the resulting formula is not only on the original variables, but also on these fresh variables. And another idea is, if we have a formula which is very small, let's say at most three variables, then we can always find a small CNF which is logically equivalent to it. And now the idea is we want to transform our big formula phi to a conjunction of many small formulas using these extra variables in such a way that satisfiability is preserved. And if we then transform these small variables to CNF, then the resulting formula is a CNF itself. More precisely, for every subformula psi, we define its name. And if the subformula is a literal, so a variable or the negation of a variable, it's just the literal itself. But otherwise, it's the name we introduced it for it, and that's a fresh variable. And now the Tseitin transformation is defined to be the CNF consisting of the following ingredients. First, we have the clause, the unit clause, just the name of the whole formula itself. And next, for every subformula, we do something. If the subformula is of the shape the negation of psi, and this negation of psi has name q, then we add q by implication, not the name of psi. That is what we add, and we make a CNF out of this. And for subformulas being a binary operation on two other subformulas, let's say psi1 and psi2, and the binary operation let's call diamond, so this can be disjunction or conjunction or implication or by implication. We introduce the following. We give the name q to the whole formula psi1 diamond psi2, and now we compute the CNF of q by implication, the name of psi1 diamond, the name of psi2. Let's give an example. Here we have an arbitrary formula in which many binary operations occur, and we have a number of non-variable subformulas B, C and D, and also the formula itself. And now the Tseitin transformation consists of the name of the whole formula, n phi, and the CNF of n phi by implication B by implication C, since the whole formula is the by implication of the formula named B and the formula named C. And next, B is the conjunction of not S and P. So we compute the CNF of B by implication not S and P, and so on. And in this way, we get the whole Tseitin transformation. Now we consider preservation of satisfiability of the Tseitin transformation. We will show that if phi is satisfiable, then the Tseitin transformation is satisfiable, and also the other way around. But first, assume phi is satisfiable. That means it admits a satisfying assignment. And now the idea is we extend this to the fresh variables. If we have a subformula psi, then we give n psi the value of this subformula. And then this yields a satisfying assignment for the Tseitin transformation. First, we had a satisfying assignment of the whole formula, so the whole formula yields true, so n phi yields true too. And if we have a subformula not psi, then we observe that Q by implication not n psi yields true if Q is the name of not psi. That is how we defined the values of the names. So this Q by implication not n psi yields true, so also its CNF yields true. And if we have a subformula psi1 diamond psi2 for a binary operator diamond, and it has the name Q, then Q by implication n psi1 diamond n psi2 also yields true by definition, by this assignment, the definition how we gave values to our n's. So this yields true, so also its CNF yields true. So we conclude that from the satisfying assignment of phi, which we extend to the fresh variables, we get a satisfying assignment of T phi. So satisfiability of phi implies satisfiability of T phi. Conversely, assume that T phi is satisfiable, and that is, it admits a satisfying assignment. And now we apply the same satisfying assignment to the original formula phi, in which only the original variables occurs and not the extra variables. But since Q by implication n psi1 diamond n psi2 yields true for a subformula psi1 diamond psi2 having name Q, we obtain that every subformula psi of phi gets the value of n psi, and the same for not n psi. And since n phi yields true as part of the Tseitin transformation, we obtain that the whole formula phi yields true, so phi is satisfiable. Combining both directions, we get that phi is satisfiable if and only if T phi is satisfiable. And now we still need to compute the formulas CNF of the small formulas we saw in this construction. And the small formulas all were of the shape, the name of the formula by implication, either a negation or a binary operator on two other variables. And that can be done as follows. If it's a negation, well, we only need to compute the CNF of P by implication not Q, and that is P or Q and not P or not Q. The only way P is equivalent to not Q is that P or Q should be true and P or Q should be false, which is stated in this formula. And by a truth table you can easily check that this is equivalent. Next we need to consider the binary operators, so let's consider P by implication Q and R. Well, that has this simple CNF, and the same for disjunction has a simple CNF, and for by implication we have this one. And we did not give the formula here for implication, but if we just write Q implies R to be not Q or R, we can use the formula for OR. These small formulas for CNF are easy to compute. For instance, if we consider the one with disjunction, P by implication Q or R. We want to transform this to CNF. How to do that? Well, first we observe that the by implication is just a conjunction of two implications, one from left to right and one from right to left. And if we consider the implication from left to right, we see P implies Q or R is equivalent to not P or Q or R, which is a clause itself. And the other direction, Q or R implies P, is equivalent to not Q or R or P. And by De Morgan rules, it can be written in this way, and by applying distributivity, we get these two clauses. So we conclude that the CNF of this small formula consists of these three clauses. And in this way, we can do all these computations. Concluding, for every propositional formula phi, its Tseitin transformation T phi is easily computed. The size is linear in the size of phi, so there is no exponential blow-up, not even a polynomial blow-up, only linear. And it preserves satisfiability. A formula phi is satisfiable if and only if T phi is satisfiable. And even more, it not only gives a CNF, it gives a 3CNF. All clauses occurring in T phi have at most 3 literals. And this Tseitin transformation is used in all current SAT solvers. Thank you.